Alright, so sorry I couldn't be with you in class today. I just wanted to make this little video in place of it. Since there are no questions, it'll go a little bit quicker than class, and I hope that's okay. Hopefully you can use the rest of the time to work on your homework. So let's get started. So the quadratic equation, or the quadratic expression rather, has the form ax squared plus bx plus c, where a is some non-zero constant, right? So I want to walk through how we can complete the square on an arbitrary quadratic. Here's how it goes. So first of all, we can factor a out. Just use your imagination a little bit. And you just got to divide by a and divide by a here, right? If we multiply this back out, we get there. That's, ultimately the judge of any factoring. Can you multiply it back out and get where you're started to? Get where you're started at, then the factoring's right. So step one. Step two is the real completing the square step, where we take half of the middle coefficient, add it to x, square that, and then to be fair we have to subtract b over 2a squared. And the plus c over a rides along. Now, if you don't believe that, well, just notice in the green here, if we take x plus b over 2a, we square it. We get x squared, and then foiling this out, we get b over a, bx over a, because we get two of those. And then plus b over 2a quantity squared. Well, if you solve that for this, which is what's actually present to start with up here, then you get x squared plus b over a times x is equal to x plus b over 2, x plus b over 2, a quantity squared minus b over 2a quantity squared, which is what I did. And then past that point, so at this point we've completed the square, all right? Now, arguably even at this point we've completed the square. And then what happens after that is I clean things up. So I make a common denominator of 4a squared. Then I use my imagination and say that, well, that's the square root squared of that quantity. Turns out that still makes sense. Well, maybe that doesn't quite still make sense in the complex sense, but even if this step doesn't make sense, the answer still actually makes sense in the complex case. But anyway, more on that in your complex variables course. Anyway, so here we go, x plus b over 2a minus that squared. Notice I brought the 4a squared outside. Changed that to 2a. Really, it should be plus or minus 2a because of the square root. Remember, I'm basically using the square root of a squared, right? We talked about that, the absolute value of a, right? But that would be plus or minus a. And the thing is, since it's squared, it doesn't matter. This outside square. Anyway, you got the difference of squares here, right? So this has the form like big A squared minus big B squared. So we know that that's A minus B times A plus B. And so that gives us this, which then if you make a common denominator, you have that. And then finally, if we set that equal to 0, then either that factor has to be 0 or that factor has to be 0, which gives us that if ax squared plus bx plus c equal to 0, that must mean that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Of course, this is the quadratic formula. The thing inside the square root is called the discriminant of the quadratic. There are other discriminants for other polynomials which are more complicated, but that's how it works for a quadratic. Generally speaking, the discriminant of a polynomial expression tells you something interesting about it. So here's the rundown. When the discriminant's positive, you have distinct real solutions. When the discriminant's negative, you have no real solutions. You actually have a pair of complex solutions. And in the middle, when the discriminant's 0, you have repeated real solutions. I suppose to be pedantic, there's always a complex solution. It's just sometimes that complex solution is just real. Technically the real numbers are a subset of complex numbers, so it's not wrong to say that there's always a complex solution. However, in courses which are mostly real, when we say that there's a complex solution, what we're really saying is that we have a solution of the form a solution of the form which is complex such that the the imaginary part is non-zero. So I will probably continue to use that usual language, but I feel like for logical, what's the word? For honesty's sake, I have to make the red comment. All right, anyway. So let's look at some completing the squares and the corresponding discriminant. 2x squared plus 20x plus 52. So step 1, factor out the 2. Step 2, take half of that, which is 5. 10 over 2 is 5, so it's x plus 5 squared. To be fair, I have to subtract the 25. Still got the 26, so when we clean that up, we get 1. X plus 5 squared plus 1 is the completed square. Well, twice times x plus 5 squared plus 1 is completing the square on that polynomial. Notice, in this case, the discriminant works out to minus 16, which says that the solution is actually complex. It's not a real solution. That's not an accident. When we complete the square, we get a plus. That speaks to the solution being complex. This time we complete the square and we get a negative. The discriminant's actually positive. That means distinct real solutions. That's not an accident. When you complete the square and you get a minus, it indicates that you've got distinct real solutions. So again, just to run through the steps, I divide the middle term by 2. Then I have to subtract the square of that, which is 121 over 4. 121 plus 40 is 80. Rather, minus 121 plus 40 is minus 81. So I got, like, 10 is 40 over 4, right? So minus 81 over 4 is what I have. And so I get distinct real solutions. Of course, I will fess up. That's not surprising, right? Because this actually factors into x plus 1 times x plus 10. In fact, the distinct real solutions are minus 1 and minus 10, which is actually easy enough to see just by factoring the original, right? So yes, completing the square is a general method, but factoring is always faster when you can do it. Here's another example, x squared plus 6x plus 9. When we complete the square on that one, we just get a square, right? Which of course you might have seen just from the start from factoring. So completing the square is kind of silly when that happens, but there it is. And when we work on the discriminant, b squared minus 4ac works out to 36 minus 36, which is 0. So this is how completing the square and the discriminant work together. When it's a plus, the discriminant's negative. When it's a minus, the discriminant's positive. When we complete the square and we just get a plain square with no constant term, that's going to be a discriminant at 0. We're going to be in double root case. Let me show you some more examples of quadratics, because quadratics are pretty important. So in each one of these, I'm going to complete the square, I'm going to solve the corresponding equation, and I'm going to factor. All right? So first of all, complete the square on x squared plus 8x plus 9. Half of 8 is 4, x plus 4 squared. Okay, so that means I have to subtract 4 squared, which is 16. Still have the plus 9. Well, 9 minus 16 is minus 7. So the minus, that means I'm going to have distinct real solutions. Here's one way you could solve that. So this equal to 0 is that equal to 0. Isolate the square, take the square root of both sides. When we do that, we have to put plus minus in. And that gives me x equals to minus 4 plus or minus root 7. Now, you could also look at that from a factoring perspective, as I do over here. This is that by completing the square. The square root of 7, rather minus 7 is the square, 7 is the square root of 7 squared. And then we have the difference of squares, so we have like a and a squared minus b squared, so we get a minus b times a plus b. That's the pattern. And of course, once I have that, then the usual factoring implied solutions gives me that x equals minus 4 plus root 7, or x equals minus 4 minus root 7, which of course is what we found up here. So, another example. Example 2, I'm going to push this up here a little bit. So, try to cover that up. Alright, here we go. 2x squared plus 4x plus 2. Factor out the 2. Complete the square. Oh, it's just a square. So that's kind of silly. In this case, it's already factored, and I don't think I remembered to solve it, but if I was to solve it, what's the solution? 2x squared plus 4x plus 2 equals 0 has x equals to minus 1 as solution, right? Because the only way I can get x plus 1 squared to be 0 is when x is equal to minus 1. Case 3, if I have x squared plus 10x plus 169, I take half of 10, I get 5, x plus 5 squared. Subtract 25 to be fair. Okay, but 169 minus 25 is 144. Use your imagination. 144 is actually 12 times I squared with a minus. And that's true because I squared is what? It's I times I, right? So by definition, that's minus 1. So if you multiply this out, you get 144 times I squared, which is 144 times minus 1, times that minus gives me the plus 144. But anyway, the larger point here is then this is the difference of squares. So again, I can do x plus 5 plus a times x plus 5, plus b, times x plus 5 minus b, thinking of that as being my b squared. Anyway, it's the difference of perfect squares form again. And then from the usual song and dance, this means that the solutions to x squared plus 10x plus 169 equal to 0 are x equals to minus 5 plus or minus 12i. Now, of course, you could also derive these complex solutions, genuine complex solutions, using the quadratic formula, if you so desired. I have nowhere used the quadratic formula because I think that factoring and completing the square is a superior method to using the quadratic formula. I used to use the quadratic formula. I make a lot of mistakes, and I've come to the realization that, by and large, I will be more successful in a larger number of problems if I do not use the quadratic formula, but instead use techniques of algebra. I'll also show you, possibly once we get to it, how to, for uglier numerical problems, there's actually equation solvers on your calculator. So if you're not going to do the algebra, I see it's probably a better method to use one of the equation solvers on your algebra if you're just after numbers. But anyway, okay. Philosophy aside here, here's another one. So I'm turning the page now from quadratic problems to looking at some of the harder algebra problems that are in the end of section, I think, 1.5. So I think if you could follow these, you should be pretty well set to try the homework. Let's get started. So x plus 5 over x minus 2 equals 5 over x plus 2 plus 28 over x squared minus 4. How do we solve this? Well, the key observation is to notice that, in fact, there's a x squared minus 4 has both the x plus 2 and the x minus 2 factor in it. So what that means is if I multiply this whole equation by like x squared minus 4, it's going to clear all these denominators. Another way to look at it is if we had more denominators, what you'd want to look for would be like the least common multiple of all the denominators as a means to clear them out. Here the least common multiple of this, this, and this is actually x squared minus 4. In any event, here's how it works. So multiply the whole equation. Sorry, I don't have a white out at the moment. But x plus 2 times x minus 2 times that, the left-hand side, equals x plus 2 times x minus 2 times the right-hand side. Then we distribute, and notice that this cancels that, this cancels with that, this cancels with that, and just leaves us x plus 2 times x plus 5, 5 times x minus 2, plus 28. And then multiplying that out, we get this, and then you can move everything to one side. So subtract 5x from both sides, I get 7 minus 5, which is 2x, and 10 minus 18 is minus 8. Great. And then, once you have a hammer, everything looks like a nail, so of course I completed the square. which is not needed here actually. But I did. I completed the square, and I got myself to x plus 4 times x minus 2. But, of course, as is often the case with these book problems, you could have just factored, because that's clearly x plus 4 times x minus 2, right? Now, once I get to that, I can see the solutions are either 2 or minus 4. But in this kind of problem, you got to be careful. When we multiply by that, remember we multiplied by x plus 2 times x minus 2. That actually doesn't make sense when x is equal to plus or minus 2. So you got to watch out for solutions of plus or minus 2 in your end solution, because they may or may not be reasonable. You actually need to go back to the original equation and see whether or not it makes sense. In this case, they don't. Well, the 2 doesn't make sense. You can't plug 2 back into the original equation. It's not in the domain of this expression or that expression, this expression or that expression. So what that means is 2 is an extraneous solution. It's just a solution that appears in our technique, but it's not real. Not really a solution, because when you go back to the original equation, it doesn't work. On the other hand, x equals to minus 4 is a legit solution. So there you go. Additional algebra example 1. Let us look at additional algebra example 2. Alright, so solve the square root of 8x minus 1 equal to 3. So this one's pretty simple. We just square both sides. That gives us 8x minus 1 equals to 9. And then move 1 over to the other side, add 1 to both sides, we get 8x equals to 10. Divide by 8, done. That's it. And of course you can go back and check that here. When you plug in 10 over 8, you get the square root of 10 minus 1, which is the square root of 9, which is equal to 3. Hooray, it actually works. It's always good to go back and check with these kind of problems. Here's another one. We're supposed to solve the square root of 3x, 3 plus x equals the square root of x squared plus 1. Well, again, it's pretty simple. We just square both sides, and in so doing, we remove the radicals and get 3 plus x equals x squared plus 1, which we can, reorder to become the quadratic x squared minus x minus 2, moving everything to the right-hand side, so to speak. Although then I write the right-hand side as the left-hand side because I like to confuse the students. Maybe you guys would write 0 equals to x squared minus x minus 2 instead of what I did. I don't know. It's the same equation. Anyway, the larger point is we can factor that into x minus 2 times x plus 1. And so x equals to 2 or x equals to minus 1 are potential solutions. Again, I have to be careful when I square the equation. I could, generally speaking, introduce extraneous solutions, but it just so happens in this case that doesn't happen. Both of these, in fact, do work if you plug them back in. Let's see here, the 2 gives us the square root of 5 equals the square root of 5. Yeah. And plug in minus 1, we get square root of 2 equals the square root of minus 1 squared plus 1, which is the square root of 2. So square root of 2 equals square root of 2. Hooray. So as I said, neither of these are extraneous. They both work. Ooh, the end. We're finally to the end. Our last example for today. And then you can go work on the glorious homework I wrote for you. Woohoo! All right, so solve the square root of 5 minus x plus 1 equals to x minus 2. So first order of business, isolate the radical. So square root of 5 minus x is equal to x minus 3. I just subtracted 1 from both sides. Now we square, and that gives us this. Foiling that out gives me x squared minus 6x plus 9. This squares to 5 minus x. So then I have a quadratic equation, not in standard form yet. Put it into standard form, we get x squared minus 5x plus 4 equal to 0. That factors to x minus 1 times x minus 4 equal to 0. So we have two potential solutions, 1 or 4. When you try out 1, it doesn't work, because when you plug in 1, you get the square root of 4 plus 1, which is 3, and 3 is not equal to 1 minus 2, because 1 minus 2 is minus 1. So this guy is an extraneous solution. It's not even in the solution set. And the other one, 4, actually works, because when you try it out, 5 minus 4 is 1, square root of 1 plus 1 is 2, but 4 minus 2 is also 2, so 2 equals 2. Hooray! That is a genuine solution. So I hope that gives you some of the tools you need to solve those kind of problems. And I think so. When we start up again, when we have class next in person, I'll try to pick up with. Let's see here. I guess what's next is section. Goodness gracious, lost my papers. I think technically modeling with equations. I'm not sure I have much to say about that section, but definitely we'll dive straight into inequalities, which is section 1.8 in my textbook. And then of course also we should cover coordinate planes and graphs and how to graph a line. You guys probably already know that. And then some things about solving equations and inequalities graphically, which I love very much, and I think you'll enjoy it too. So anyway, sorry I couldn't be with you guys today. I had to be at my parents' house. My father's burial is today, so I need to go to that. But I should be back in school Wednesday if all goes well. So thank you. And again, you can email me any questions if you have them. I will hopefully check email Monday and Tuesday. So thanks, guys.